We defined integrals in order to compute areas, but there are many other applications of integrals. Integrals can be used to compute many other things. In this video, I want to revisit the definition of Riemann integrals and reinterpret the notation we use with a different geometrical flavor, and this interpretation will be very useful in other applications. Specifically, I will try to use the same idea to set up volumes as integrals. Let's recall the idea we used to define Riemann integral. I have a region here whose area I want to compute. It is the region surrounded by the graph of the function f and the x-axis from x equals a to x equals b. I want to compute its area. To define Riemann integral, first we break the interval ab into smaller pieces using a partition, and this breaks the region into slices. To make this process useful, I should have many slices very thin, but to make the picture visible, I'm using only 6. And then I'm going to approximate each one of the slices with a rectangle. I'm being a bit vague about exactly which rectangle. Now I'm going to write an equation for the area of all those rectangles. I'm going to look at one rectangle. First, let's say this one. I'm going to call the width of this rectangle delta x. And then the height of this rectangle is f of x for some value of x. Is some value of the function f. And I'm not being very precise about which value, but therefore the area of this rectangle is going to be f of x delta x. And now if I add over all the pieces, if we put a sum here, then I get the sum of the areas of the 6 rectangles. That's an approximation for the area of the region I'm interested in. Now, if my function is nice and integrable, perhaps continuous, then when I take the limit as delta x goes to 0, as those rectangles become thinner and thinner, then this approximation becomes exact, and that's what we call the value of the definite integral. I have been very hand-wavy here, but if we want to recall the precise formal way to do it, we spent quite a few videos doing that. What I want to do next is I want to reinterpret this notation in a way that is not very precise, but is geometrically very useful. Since the integral is the limit of sums, I'm going to abuse notation and think of the integral as an actual sum of infinitely many pieces which are infinitely small. Or more precisely, when I write dx, I'm going to think of dx as a delta x that is very tiny. The technical term is infinitesimally small. And then of the integral as the sum over infinitely many of those pieces. What do I mean by this? Here is the same region again. This time, instead of breaking it into 6 slices, I'm going to break it into infinitely many slices, which are infinitesimally small. I'm going to draw only one of them. Now, I drew a piece that looks big, that looks finite, because it's the only way to see it, but we should pretend that this is infinitesimally small. I'm going to call the width of this piece dx to indicate that. I drew only one, but I'm thinking of all the infinitely many pieces like this. And I'm looking now at the area of this slice. Now, since this is infinitesimally small, so will the area be. And therefore, I'm going to call its area dA, because it's also an infinitesimal. Now, in this case, I'm going to say that when I pretend that this is a rectangle, it's not an approximation, but is exact. And here is why. If I calculate the area of this slice by a rectangle, then the error I'm making is just this piece. This is the error I'm making if I replace it with a rectangle. But if this dimension is infinitesimally small, then the error is infinitesimally small squared. So by comparison, when this is very tiny, it's negligible, it's not important, and I can omit it in the limit. So this area is equal to the height of the rectangle, which is f of x, times the width, which is dx. And now, the area of the full region is going to be the sum, in quotes, of all these pieces, infinitely many of them. But that sum is what we call an integral. Or in other words, is the integral from a to b of f of x dx. This was a bit hand-wavy. It can't be made rigorous, it can be formalized, but I don't want to do that. For our purposes, this is okay. The advantage of thinking of it this way is that it helps with the geometric intuition, and it helps us reuse the same ideas for many other applications of the integral, apart from areas. For example, It is useful to think of integrals this way to figure out how to use integrals to compute volumes. This is a carrot. Let's say I want to compute its volume. If I don't know what else to try, maybe I can start by approximating it by a cylinder. It is definitely not a cylinder, but it's close, and that will give me a certain error. But let's say I want something better. Well, just like we did with areas, we took an arbitrary region and sliced it and approximated the pieces with rectangles. I can also take this volume and slice it, literally. And now look at what we got. If I take any one of the slices, well, this is pretty much a disk. It is not an exact disk, but it's very close. This is pretty much a disk, and I can approximate it by a disk, and I know how to compute its volume. And if I take some kind of limit, as the thickness of the slices goes to 0 and they become infinitesimally small, this will no longer be an approximation, but it will give me the exact value of the volume. I'm going to make that specific with a concrete algebraic example. Here is a concrete example of a region whose volume I'm going to calculate. I'm going to call R the region on the first quadrant between the graph of y equals x squared and the x-axis from x equals 0 to x equals 1. And I'm going to rotate this region around the x-axis. This creates a solid, and I want to compute the volume of that solid. At this moment, I invite you to pause the video, draw a picture, and try to understand what this region looks like. What does this volume look like? Once you are comfortable with that, keep watching and I will explain how to set this up as an integral. This is the region R between y equals x squared and the x-axis from x equals 0 to x equals 1. So this is the region. And I'm going to rotate it around the x-axis. So when this is rotated around the x-axis, it creates a solid. And it's going to look a little bit like this. It's kind of like a cone that has been bent a little bit. Now I want to compute the volume of this solid. And to do that, I'm going to slice it into pieces. Infinitely many pieces, infinitesimally small. I'm going to draw one of the pieces. And to do that, let me cut a thin slice of the region R here. I'm going to say the width is dx because I'm pretending it's infinitesimally small. I'm drawing it as a finite piece because it's the only way to visualize it, but assume it's microscopic. And then when you rotate it here, this will correspond to a slice like this one. Now, I want to figure out what the volume of this slice is. And I'm going to call it dV because since the slice is infinitesimally thin, the volume will also be infinitesimally small. Now, what is this piece? This is pretty much a disk. It's not exactly a disk when this is finite, but in the limit, when this is infinitesimally small, I can approximate it by a disk because the order I'm making is negligible. So the volume of it will be the volume of a disk. Now the volume of a disk is the surface area times the thickness, or height in this case. Now the height in this case is dx. So the volume of this piece is dx times the surface area. And if I call this radius r, then the surface area is pi times r squared. Now, let's see what r corresponds in the original picture. Knowing where this comes from, r is this, which is equal to y, which is equal to x squared. This is just in this specific case. So, I have a way to write the volume of an infinitesimally thin piece, and then the volume of the whole thing will be the sum, in quotes, of all those infinitesimally thin pieces, but that's actually an integral. Since I am using x as the variable, the integral goes from 0 to 1. And now the integral of the volume of this piece, which is this equation. Now instead of r, I'm going to put x squared because I'm using x as the variable. And that's it. I have succeeded at setting up this volume as an integral. Now we can go ahead and use antiderivatives to compute it. I will leave that part as an exercise, but you can perform that computation and the final answer should be pi over 5. To conclude this video, in case you want to practice this method, here are 4 examples of solids whose volume you can compute with exactly the same idea as I have used in the one example in this video. The calculations are more complicated, but the idea is the same. They are all carrots that you have to slice infinitesimally thin.